Okay, hello everyone. So in this video, we'll be looking at an exercise where we're asked to minimize a DFA. So this is the DFA that we want to minimize. So just as a quick reminder before we start the exercise, um, how do we sort of do DFA minimization? So let's just write a quick DFA minimization reminder. So the whole idea behind the minimization algorithm is there's this idea of distinguishable versus indistinguishable states. So for the purposes of this video, I'll write distinguishable states, pairs of distinguishable states using this like bow tie symbol, and indistinguishable states using this squiggly equal symbol. And the idea is that what the minimization algorithm should do is it should find all pairs of indistinguishable states, and it should place states um, P uh, states PQ where P is indistinguishable Q into the same set of states PQ. Maybe there's other stuff because maybe um, there are maybe three states which are all sort of pairwise indistinguishable from each other. And so what the minimization algorithm should do is it should identify pairs of states which are indistinguishable and then place those states which are indistinguishable, like I just said, into some set of states which um, will act as a single state, as a single state in the minimal DFA. And remember, I can say the minimal DFA because uh, minimal DFAs are unique up to sort of renaming of states. So once you found a minimal DFA for a given regular language, you've actually found the only minimal DFA for that regular language, modulo sort of renaming the states with sort of different symbols, right? And so this is the idea behind the minimization algorithm. It's to find essentially states. So maybe these two states are indistinguishable. And the intuition is that if two states are indistinguishable, it means that they're kind of doing the same thing or encoding the same information. That's why, you can't sort of distinguish between being in Q1 or Q3. The behavior of the DFA is going to be the same regardless of whether you're in Q1 or Q3, right? And so if that's the case, then actually in a minimal DFA that has no redundancy, Q1 and Q3, for instance, should be together. I'm not saying they're necessarily going to be together in this in the corresponding minimal DFA for this guy, but if they were, then they should be sort of together in the minimal DFA, acting as kind of one. Okay, so then that's great in terms of intuition. How do you actually find indistinguishable and distinguishable pairs of states? So there's kind of this is sort of a recursive procedure where the base case or the initial condition for distinguishability, I'll say, is if pairs of states um, are not both accept states or are not both non-accept states. So the initial condition for pairs of states P and Q to be indistinguishable is either the first element of that pair, the first state in that pair of states is an accept state and the second one is not, or vice versa. So the first one is an accept state and the second one, or sorry, so in this first case, the first state in the pair is an accept state and the second one is not, vice versa in the other one. So in this case, the first element of that pair is not an accept state and The second one is. I think I might have confused them at the beginning. So just to be clear uh, with the notation and with what I'm saying, so making sure that these two things kind of align because that's important. So this is the initial condition, and that's how you find the first pairs of states which are distinguishable. And now once you do that, then you can kind of sort of recursively find more and more states which should be distinguishable from each other. So the way to do this, so this is kind of like your base case in your minimization algorithm. The recursive case or the recursive condition, what if both the pairs of states are accept states or both the pairs of states are non-accept states? Does that just mean that they're um, immediately indistinguishable? No, right? Like it's very possible for this state and this state, both are non-accept states, to be distinguishable from each other, right? Maybe it matters whether you're here or here, and so you don't want to merge these guys together, right? And so how do you check this, right? That's the question we're asking here. That's through this recursive condition that I'm going to write down. So essentially, the recursive condition is P is distinguishable from Q if there's at least one letter in the alphabet, such that when you read that letter from P and you read that letter from Q, you go to states which are themselves distinguishable from each other, right? So maybe P and Q are both accept states or both not accept states. But right, maybe if you read A from P and A from Q, maybe you go to an accept state here and a non-accept state here. In which case that also means that P and Q are distinguishable. And now you kind of recheck this condition as long as you're finding more and more distinguishable states, right? So for instance, if you had a case like this, right, then now you know that P and Q are distinguishable. So that means that if I read an A from the states R and S, well, R and S will go to P and Q are now distinguishable. So the distinguishability sort of bubbles up to other states that are connected kind of in this way. Okay, so that's the general idea as a reminder. Now to actually do the minimization algorithm, you it's a bit easier if you have some kind of table, which is what we're going to use as a kind of data structure to make this process a bit easier. So let's just copy this state transition diagram again. Okay, so you're going to see why this is important. So what I'm going to create is I'm going to create a 2D table where I'm going to have every possible pairs of states as row and column entries, and then I'm going to mark in the cells whether the states are distinguishable or not, right? So let's do that. Q0, Q1, Q2, Q3, Q4. And again, Q0, Q1, Q2, Q3, Q4. Okay, so let's make this a proper like grid-like table so we don't get lost. So let's do this. Let's do this like this. Okay, now it looks like I have a table. This looks like a table to me. And the nice thing about this algorithm and about distinguishability is that it's kind of commutative, right? So if a P is distinguishable from Q, then this implies that Q is distinguishable from P. So that means that I don't have to do the whole table. I only have to do the lower or the upper half, right? It's whichever you kind of want. I'm also not going to do the diagonal because, of course, a state is indistinguishable from itself, right? It'd be a bit weird if a state encoded different information from itself, right? Than its own state. So what I'm going to do then is I'm just going to focus on the lower quadrant or lower triangular part of this matrix or of this 2D array. Okay, so now I have my table now, and I know what area to focus on. The next thing that I like to do when it comes to the minimization algorithm is I just like to annotate on the sides whether the state I have is an accept state or not an accept state. So let's see, Q naught is not an accept state, Q1 is an accept state, Q2 is not an accept state, Q3 is an accept state, and Q4 is not an accept state. And it's the same thing, right? So this is just like, it's the same exact um, sequence or membership for the columns because they're the same as the row entries. Okay, so we get this. Now you might be asking yourself, like, why did I bother to do this? Well, because now I can very quickly check, the initial condition, right? The initial condition, which is that um, P and Q are distinguishable in sort of the base case if P is in an accept state and Q is not, or vice versa, right? So, I see that Q1 is an accept state and Q naught is not. So I will mark distinguishable states with an X. Q2 and Q naught, those are both non-accept states, so I'm not going to mark it. Q3 and Q naught are different in terms of accept states, so I'm going to mark it. And I'm going to redo this for all the other pairs of states that are not accept, non-accept states. Okay. Okay, so now this is sort of like I did the base case in purple. Now the next thing to do is start doing like the recursive case, right? Where I'm like checking whether even though I'm both an accept state or both non-accept states, I might go to pairs of states that are distinguishable. So to do that, let's start with this entry here. So what I'm going to do is I'm going to check whether Q naught and Q2, whether, when you read a letter, any letter, you might go to two states that are themselves actually distinguishable. This is what I'm going to check. In other words, I'm going to check if using the same letter, I go to pairs of states that are already marked by an X, right? If they're not marked by an X, then I can't say anything. If they are marked by an X, then that means that they're distinguishable. Okay, so let's do that. Let me recopy this. Okay, so I'm recopying this. And I'm looking at my table. So I'll do Q naught and Q2. So delta Q naught and delta Q2 when reading an A. So delta or Q2 when reading an A, that's I go to Q1, right? And delta Q naught when reading an A. Okay, I see. So it looks like there's a transition missing here, right? So this happens sometimes. Sometimes people are a bit lazy when they write their DFA. Strictly speaking, what's actually going on is there's an extra state here where when Q naught reads an A, it goes to, let's call this Q5, where Q5 is a dead state, right? Okay. So no big deal. We just have to kind of expand our table a bit more before we actually get cranking with this algorithm. So let me just expand it on the fly here. So let's add Q5 as a row. Let's do this like this. And yeah, I'm not going to add it here because, it's already Q5 with all the other states except Q5, but, I don't need to check that actually. And Q5 is not an accept state. So I can add some more X's based on my base case. So I'm going to add, um, let's see, I'm going to add an X here and here, it looks like. Yeah, it looks right, right? Because like this is not accept state, this is not accept state, so these guys should remain unmarked for now for the base case. Okay, nice. So we saved that a little bit. This sometimes happens, you don't necessarily think to check whether there are any omitted transitions in a DFA. If there are, then it just means that they go to an extra dead state. But now I can actually do what I kind of wanted to do in the first place, which was to check whether Q2 and Q naught were distinguishable, right? So let's see, Q2 and Q naught. Um, so Q naught, when it reads an A, it goes to Q5. And Q2, when it reads an A, it goes to Q1. So now the question is, are these two distinguishable? Well, if I look at my table, Q5 and Q1 is here. There's an X that's marked, so that means that they are distinguishable. So these guys are distinguishable. And so therefore, this implies that Q naught is distinguishable from Q2. And so for this first phase in my recursive case, I'll use green. So step one of recursive case. So I mark this with an X, right? Okay. And I'm gonna repeat this for every pair of states. So I might go a bit faster though, just for uh, the sake of your time. But I encourage you to like pause the video and maybe check for yourself where the X's should be for this first step, right? Okay, so let's see. For Q4 and Q naught. So Q naught, when you read an A, you go to Q5. Q4, when you read an A, you go to Q3. Q5, Q3, that's distinguishable, so I'll add an X. What about Q5, Q naught? So Q naught, when you read an A, you go to Q5. Q5, when you read an A, you also go to Q5. So, okay, that means that it seems so far that it's indistinguishable, but we also have to check B, right? So Q naught, when you read a B, you go to Q3. Q5, when you read a B, you go to Q5. So Q5, Q3, that's distinguishable, right? So that means that I'm also going to mark this. Okay. Let's do the same thing for Q1 and Q3. So for Q1 and Q3, when you read an A, you go to Q naught here, and when you read an A, you also go to Q naught. So of course, that means that so far they're indistinguishable because um, the same a state is indistinguishable with itself, right? What about when you read a B? So Q1, when you read a B, you go to Q2, and Q3, when you read a B, you go to Q4. Let's look for Q2, Q4. So Q4, Q2, Q4, Q2 is unmarked. So like this is a bit subtle, but when it's unmarked, it means that you can't actually conclude, right, that you go to pairs of distinguishable states. So that means that you should leave it unmarked. So leave Q1, Q3 unmarked because when you read an A, it goes, I think we said they both go to Q naught. And then when they read a B, then they go to Q2, Q4, which is unmarked, right? And so therefore, we cannot conclude at this stage of the algorithm that Q naught, Q3 are distinguishable, right? So I'm going to leave this unmarked for now, right? So this cell is going to be unmarked. What about Q4 and Q2? So Q4 and Q2, it's actually going to be the same deal. So Q4 with an A and Q2 with an A, you go Q1, Q3. So that's still unmarked. and Q4 with a B, Q2 with a B, that goes to Q1, so the same state. So that means that, again, I don't have any evidence to mark this, right? What about Q5, Q2? Q5, when it reads an A, it goes to A. Q2, when it reads an A, it goes to Q1. And I already know that Q5, Q1, right? Q5, Q1, that's distinguishable, so I can also mark this guy. Very nice. Well, let's use the same color, green. Um, Let me actually just charge my iPad. Okay, so let's do the same thing for Q5, Q4. So for Q5, Q4, when you read an A, you go to Q3. When you read an A, you go to Q5. Q5, Q3, that's marked. So I get to mark this guy again. So this kind of makes sense. Why? Because this means that Q5 is distinguishable with all other states, which, like I said, kind of makes sense because the role of Q5 is to be a dead state. The role of all the other states is not to be a dead state, because a dead state is one where you just can't escape. It's a black hole. None of these other states are kind of like black holes, right? So that's kind of why they're not indistinguishable from Q5. Okay, so that was step one, right? Step one of the recursive case. Now we're essentially just going to do the same thing again for step two. So step two. Oh, that's I already used purple. Um, of the recursive case. So step two of the recursive case is really just going to be about um, Q3, Q1, and Q4, Q2, right? So for Q1, Q3, when you read an A, you go to Q naught. Again, they're the same. So like Q naught is the same state, so it's indistinguishable from itself. So you can't use that as evidence for distinguishability. Then Q1, Q3, when you read a B, you go to Q4, then you go to Q2. So this is the only other unmarked cell, which means that that's again not evidence for distinguishability. So like this might seem repetitive. It's important for you to redo this because it's possible that like maybe in the last step you had found that Q3 and Q1 was indistinguishable because this was unmarked. But it's possible that in the next step this had actually been marked, and so then you would have concluded that actually Q1 and Q3 were also distinguishable, right? So it's important to redo this step. Um, so it looks still that for step two, Q1 is distinguishable from, or sorry, um, let me write cannot mark Q1, Q3. And is it going to be the same thing for Q2, Q4? For Q2, Q4, I have with an A, I go to Q1. With an A, I go to Q3. Those are unmarked, so no evidence for marking. When I'm at Q2, Q4, and I read a B, I go to Q1, and I go to Q1 again, same state, so it's indistinguishable. So again, that's not evidence for marking. So again, cannot mark Q1, Q3. And now essentially we're starting to get to the stopping condition of this algorithm. So the stopping condition of the minimization algorithm when there is no change in the table from step n to n plus 1, which has kind of happened, right? Because at the end of step 1, really this is, yeah, because step 0 is like the base case. At the end of step 1, we had this table. right? We have this table. Then at the end of step two, right, which we just did here, we still have this table, right? So here there's essentially no change, which tells me that I should stop um, the minimization algorithm. And now I can actually build my minimal, DFA. Okay. So this is the last, essentially the last step of the minimization algorithm is actually, well, let's build. So now we can build the minimal DFA. And the way that we build the minimal NFA, blah, blah, the way that we build the minimal DFA is we take all the pairs of um, for all of the sort of pairwise indistinguishable states. For each group of pairwise indistinguishable states, you create a set of states which becomes a state in the minimal DFA. So here it looks like Q1 and Q3 are going to be indistinguishable because they're unmarked at the end of the algorithm. And the same thing for Q2 and Q4. So actually I can also signal this by maybe adding a circle in both of these cases. Um, so that tells me that I should have Q1, Q3 as one state in my minimal DFA, Q2, Q4 as another one, and then all the other states that aren't grouped so far should be in separate states. So that's going to be Q0 and Q5. Okay. So now these are my states. These are my states. Um, Now the start state is going to be um, the set of states that contains the start state from my initial DFA. So from the DFA I began with, which in this case was Q1, right? So it's a bit confusing because Q naught is marked here, but actually the start state is Q1. So that tells me that the start state here should be this guy. Then what about accept states? So a set of states in the minimal DFA is an accept state if it contains any accept states from the original DFA. But this is kind of quite convenient because in this case, right, so this doesn't necessarily always happen, but in this case, all of the states, um, which were accept states in the original or the DFA that we started with, are grouped together in the minimal DFA. And in fact, that just means that this is going to be the only state that is an accept state. Okay. And then for the transitions, it's essentially transitions from set of states to other set of states, where you can actually use any state in this set to determine where to go next, because the the states in a given set of states are indistinguishable. So it doesn't matter which one you pick, you're going to actually go to the same place no matter which of these you use as the representative. So for instance, for Q1, Q3, it would be nice to have this image again. Yes, okay. So for Q1, Q3, it looks like when it reads an A, it goes to Q naught, and when it reads a B, it goes to Q2, right? Well, I'm just looking at Q1, but if I was looking at Q3, you would go to Q4, but that's in the same set of states. And it's kind of always going to work out this way. So the same thing for Q2, Q4. Q2, Q4, when you read an A, so this was for B, when you read an A, you'll go to um, Q2, Q4. Oh, when you read an A, you'll go to Q1, Q3. And I think same Q2, Q4. Yeah, same if you read a B, right? Because you're at Q4, you're at Q2, you read a B, you go to Q1, which is in here. Q5, unsurprisingly, that's just gonna loop back to itself. It's a dead state. And the only way to actually get to Q5 is with Q naught, right? So Q naught, reading an A goes to Q5, and reading a B goes to Q3, right? Okay, and so this now is my minimal DFA. So it has four states instead of one, two, three, four, five, six. So we've kind of been able to prune out two states or merge together two pairs of states together to create single sets of pairs of states in this case. Okay. Um, and so yeah, that's how you run the DFA minimization algorithm.